Hello, welcome back to another bizarre concept in math. I am happy to have you here on my channel. Please, I hope you enjoy this one. So what we're going to be doing today is that we're going to be proving the DeMoivres theorem, all right? DeMoivres, some people pronounce it differently. I said DeMoivres theorem. So we're going to be proving DeMoivres theorem, all right? And before we get into it, let's just refresh ourselves of complex numbers. So we know that a complex number takes the form z is equal to a plus bi. Z is equal to a plus bi, where a is the real part of that number and bi is the imaginary part. All right. And by now we would have been able to plot our complex numbers on our organ diagram, where we have the x-axis being the representing the real axis and the y-axis representing the imaginary axis. And here we have our point z is equal to a plus bi. All right, and we know that this line here would be the length of z here. It would be the length of z. All right, and we're going to call that length r. Now, between the length of z here, between r and my real axis, there is going to be some angle, and we're going to call that angle theta. All right. Now, this distance here that we want to move from here to point Z. We want to move from my point of origin here all the way up to point Z. And we know in order to move from one point to the next on our graph, we must first move along our x-axis and then our y-axis. In this case, however, we're first moving along our real axis and then our imaginary axis. All right, so we're moving along our real axis, and this distance is going to be called A. And then we're moving along our imaginary axis. We're moving along our imaginary axis, and we're going to call that distance B. Looking on what is happening here, we move along our real axis and we move along our imaginary axis, forming somewhat what we'd call a right angle triangle. Now, this distance A is going to be equal to r cos theta, r cos theta. And this distance B is going to be equal to r sine theta. Now, remembering that we're moving along our imaginary axis, this distance is going to be equal to r sine theta times I. All right? R sine theta times I. Now, here, we know that z is equal to a plus bi. Z is equal to a plus bi, and that is the general form of writing a number in writing a complex number. That's the general form that we express our complex number, a plus bi, where a is the real part and then bi is your imaginary part. Good. Now here, we know, however, that a is equal to r cos theta and b is equal to r sine theta times I, because we're moving along our imaginary axis. So what we can do is we can replace A with R cos theta. And that's what we're doing here. We replace A with R cos theta plus we're replacing B with R sine theta and replacing our imaginary number. All right. So BI is going to be R sine theta times our imaginary number I. So Z is equal to R cos theta plus R sine theta times our imaginary number. Now looking at what I have here, I can factor R, I can factor it out. So I'm going to do that. I'm going to go ahead and I'm going to factor out R. So Z is equal to R times cos theta. I put my I in front, So it's R cos theta plus I sine theta. And this here is how we write our complex numbers in polar form. It's how we write our complex numbers in polar form. And this was proven by DeMoivres, and that's why it is called DeMoivres Theorem. What we've just done is prove DeMoivres Theorem of how we can express a complex number in polar